Maybe we can start a little early. So the next speaker is Graeme Baker from Princeton. So you can start.
And can everyone hear me all right? I just want to make sure with GatherTown.
Yeah.
Okay, perfect. Hi, everyone. I'm Graeme Baker, and this is joint work with my advisor, Mikhailo Shkolnikov. This is the title of the talk. I'm programming applied in computational mathematics at Princeton. Misha, I think he's affiliated with PACM, but I think he's in his main gig is operations research financial engineering. But anyways, so let's get started. So the Stefan problem was originally formulated by Stefan to look at the freezing of water. And we're interested in the supercooled Stefan problem, one phase and one dimension. So here U denotes the temperature below equilibrium for our liquid, and it satisfies the heat equation. And the action is taking place on this domain gamma. So lambda here is the boundary between solid and liquid, or ice and water, if that's the classic case you're looking at. We have some initial temperature distribution F, and it's greater than 0 everywhere. And since it is the temperature below equilibrium, that means indeed we're cooled past the equilibrium temperature. At the boundary, we have this equilibrium condition that says that the water freezes onto the ice at equilibrium temperature. And then the motion of the boundary is governed by the Stefan condition, which says that the rate of change of lambda is proportional to dx of u at the boundary. And this constant of proportionality is the latent heat of formation. So I would show a video, but I've learned the hard way that videos work very poorly over Zoom. But for the supercooled problem, you can go and look on YouTube, and there are people who take water bottles, put them in the freezer, and then you can knock it, and you'll see the freezing happens quite quickly. And so just looking at the vertical axis, this would be our model for one phase and one dimension. And so I just mentioned that it happens quickly, and a difficulty with this problem is that you can actually have finite time blowup for lambda prime. And this makes it interesting to study. And so our goal is to realize the limiting boundary lambda as some limit of regularized boundaries lambda epsilon. So I just said that lambda prime may blow up. So what does that mean to have some limiting boundary lambda? That is covered in this slide. So prior work. So this is a paper with my advisor. And this is a probabilistic formulation for the limiting problem. So you can encode the initial temperature distribution into this random variable x0 minus. And then you need to find a pair, x and lambda, that solves the following problem. So x is a Brownian motion starting at x0 minus, and it has drift lambda. You look at the stopping time tau, the first time that x hits 0. And then lambda is described by the probability at a given time that tau is going to be less than that time. And so given a solution to this, you shift things around. So PTX are the densities for these random variables involving x and the stopping time. And then you shift the domain, and then you get a weak solution to the original PDE. And so if lambda prime, if you can show that this doesn't blow up, then you have a bona fide solution. And so one of the things that's shown is existence and uniqueness for this. Uniqueness holds if you blowups may occur, and so actually this extends the notion of solution, because you could have lambda spiking, but then if you fix the jumps to satisfy some energy conditions so that the jumps are minimal and the energy is conserved, then you have uniqueness. And if you also have that the initial heat distribution isn't too cold at some point, then this limiting solution here is also continuous. Okay, so this is the limiting problem, and now we look at our regularized problem. So U sub epsilon, this is going to be the regularized. We're still looking at the heat equation in this domain here, and our regularized boundary is lambda epsilon. We're going to regularize the initial condition as well, and this is just technical, and we'll take the smoothing kernel to the Dirac as epsilon goes to 0. And we've replaced the equilibrium condition here with this, which is the kinetic undercooling condition. So this is kind of the key to our work. And there's a couple interesting things we can get out of this. So if, as epsilon goes to 0, if this lambda prime doesn't blow up, then the right-hand side intuition-wise we can think of as going to 0, and we'll get back the equilibrium condition. But also, if we divide through by epsilon, then we see that for a fixed epsilon using the maximum principle, lambda epsilon prime will be bounded by the maximum of u epsilon divided by epsilon. And then we have here, again, the Stefan condition. So this looks a little bit different from 2 slides ago. Before we just had alpha lambda prime is dx of u. Now we've put alpha minus 2u. Before we did have the equilibrium condition though that said that u at the boundary is 0. So this is equal, but I'll go into this a little bit more because before we tried working with the regularized problem without this minus 2u, and it's not as amenable. So let's talk about this latent heat. This was one of the more adventurous parts of this project. We went into this reference here is applied chemistry literature to figure out how to do this thing. We actually reverse engineered it, and then we learned that this is something that engineers do. So this delta HF is our original latent heat of formation alpha. And our Stefan condition says that the latent heat times lambda prime is dx of u. And then what we're doing is we're allowing our liquid to supercool at the boundary. And so we'll just draw a line down according to that slope and subtract that from alpha. And that's exactly what alpha minus 2u is. The 2 is the heat capacity. And it's 2 because we want there to be a 1/2 in our heat equation, because that's the heat equation that probabilists like to work with. Also, we need this latent heat to be positive. And so we enforce that the initial condition isn't colder than alpha over 2. And then using the maximum principle, that will enforce this for you at all times. Okay. So here is the result, and I'll go through it sort of piece by piece. So for each epsilon, we can solve this regularized problem, and we get back this bound from the kinetic undercooling condition. So there's a unique solution. Also, we have a very nice monotonicity property that we can show. So that as epsilon goes to 0, these boundaries increase pointwise. And their pointwise limit solves the original problem. And then from that original problem, under our assumption with the initial distribution, we have continuity. And so because we're increasing pointwise to this continuous function, we get uniform convergence on compact sets to the ladder. So this is a probability seminar, and this looks like a lot of PDEs, but I swear there's probability under the hood. So let's look at a hint of the proof. So just like with the x's and lambdas from the probabilistic formulation, now we're going to have an x epsilon. And so what do we do? We're looking at the same process. Here, because of the regularization, we don't need an x0 minus. Things trying to be continuous. But we look at this Brownian motion, start at the distribution of the negative temperature, and we're subtracting off our boundary. And instead of looking at the stopping time at 0, now what we do is we reflect this process. So psi here is the Skorohod map. And we look at the local time of the process at 0. And so the big tool that we use, and you can phrase it also in PDE terms, but for showing that goes to the limiting problem, it's quite nice, is this Feynman-Katz formula. And so we can, for any epsilon, we have that lambda epsilon is some functional of this local time process. And so I have this arrow here. This converges to the probability that tau is less than or equal to t, which was lambda t from the original problem. This, you have to be careful here, but basically what you do is you write in this expectation, you split up into the set where tau is less than or equal to t and where it's greater than t. And then on that set, because of the monotone convergence that we have, we can play around with the local time and the probability of this hitting time occurring. And so this guy here, we can kind of look as we take the limit epsilon to 0, goes just to this indicator event of tau less than or equal to t. Okay, thank you. And I have a little bit of time for questions.
Okay.
And here are the references.
Thank you very much, Graeme. As he said, he does have a little bit of time for questions. So if anyone has some, please just unmute yourself.
And I'll throw up a future directions slide in the meantime while people are thinking.
So everything you're doing is in the continuous setting. There are presumably nice discrete models that should be describing or described by this.
Yep.
How much is known about what happens there? It's a different type of regularization.
Yeah. Yeah, there's particle models on the integers, and then you're looking, like particles of water distributed according to the initial heat distribution. And then as they jump and hit this free boundary, it increases. And you can show that this, as you scale, this converges to the same lambda from this work here. And so it's kind of nice that you can regularize things in the PDE sense and then take the regularization off and get back this lambda. Or you can look at this, discrete model and also take the limit and get the same lambda. And so it kind of shows that this is the right idea of a generalized solution to this problem.